To explain exponential growth and decay, I'm gonna do an introduction first about what this model represents. So let's start with two bunnies. Let's say that the population, which would be y of bunnies, okay, so it's y is number of bunnies, starts with 2, and then they add one bunny every, let's say, 3 years, which is not really true because they definitely add more to the family in a lot less time than that, but let's just, for demonstration purposes, they add one bunny every 3 years. So that means our variable x is in years. So for any number of years, I can determine the number of bunnies that there will be. Not only that, but this model is saying that these are the mother and father bunnies, and they are the only ones who are allowed to reproduce. So in this case, this is probably not very close to the truth, because you know that as time goes by, those baby bunnies become fathers and mothers on their own. So in that situation, a linear model will definitely not fit our purposes. But just let me show you what this model looked like, and let's talk about the rate of change then. So in this demonstration, we have our equation. We have two bunnies at the beginning, and we're adding one every 3 years. And this would be the graph. Obviously, we have a line. And you can see the rate of change does not change at all. It's constant. It doesn't matter in what points in time I measure the rate of change. Let's say between 5 and 10 years. The difference on the population over time is still the same, 1/3. So no matter what 2 points I'm measuring in time, this rate of change does not change. That's why we say that in linear functions the rate of change is constant, and it will be this number all along. So now let's let's change the model for these two bunnies. Let's say that the number of bunnies doubles every year. So at the beginning, when x is 0, at the beginning I have 2 to the 0, which is 1. So I have to multiply this by 2, because at the beginning I want at the beginning of time I want to have 2 bunnies. So when x is 1, I have y equals 2 to the 1 times 2, which gives me 4. When x is 2, y is 2 squared times 2, and that will be 8. So as you can see, as time goes by, the population starts doubling. It starts with 2, and then it goes to 4, to 8, to 16. So this is called an exponential model. And as you remember, the function looks like this. And in this case, because the population is doubling, this is exponential growth. In case was the population wasn't growing for some reason, maybe some kind of disease, then this would be decay. That's what decay looks like, and that's what growth looks like. The rate of change definitely starts changing. It's not going to be the same. Whenever I'm finding the average growth or the growth rate, is really changing, and I'm going to show you with this application. So I'm measuring the rate of change in here between year 0 and year 1, and I have my secant line, and I can find the slope, and the slope here is 1/1. Then I want to measure the slope between years 1 and 2, and now it's 2/1. Now I want to do it between year 2 and year 3, and now I have 4 over 1. And then between 3 and 4, I'm going to have 8 over 1. So guess what would be the rate of change between 4 and 5? It's going to be double of the previous one, which is 16. So what would be the rate of change between 5 and 6? It will be double of 16, 32, as you can see that. So the question is, does this work for any exponential function if the base is not 2? So I'm going to change it to base 3 because that's where the change is noticeable. And then let's start from the beginning again. Between 0 and 1, let's say that the rate of change is 2. This is the first rate of change at the beginning, so it could be any number. If I rewrite this equation, it probably would be different. But let's see how the next one is going to be. Between 1 and 2, it went from 2 to 6. So guess what would be the next rate of change between 2 and 3? 18. So it went from 2 to 6 to 18. So it's growing by 3 again. So now between 3 and 4, I think I'm going to have 3 times 18, which is 54. And between 4 and 5, 3 times 54, which is 162. So this is true for any exponential function, no matter what the base is. I'm going to stick with integers because those are the ones that we can really tell how the rate of change has changed. With decimals, you won't have to have a calculator. So in here, between 0 and 1, you have a rate of change of 3. The next one is going to be 12 because 3 times 4, 12. And then the next one between 2 and 3 is going to be 12 times 4, which is 48. So the rate of change in here, the average rate of change, is changing by a factor the same as the base. If this equation right here is 4 to the x, so the base is 4, so that's why the rate of change is changing by a factor of 4. Another thing that I wanted to point out, if instead of 4 the base is 5, and I start again at the beginning, notice how as time goes by, the slope of that secant line is growing a lot faster now than it did when we did base 2. In here, base 2, it started at 1, and then 2, 4, 8, 16, 32. But if we're using, let's say, base 6, then this definitely is growing a lot faster. So there are a few conclusions that we can draw from here. One of them is that if the population is small, then the slope of this secant line, meaning the average rate of change, is gonna grow slower than compared to a population that is bigger. So in other words, if you start with few bunnies, those bunnies are gonna increase at a slower pace than if you have a lot more bunnies. The takeaway of this introduction, exponential function is a more reasonable model whenever we're talking about population. And in the exponential model, in the exponential function, the rate of change does not stay constant, it changes. And then the other takeaway is a small population increases slower than a bigger population.